The Defense Advanced Research Projects Agency, or DARPA, has developed the Space Surveillance Telescope to enable much faster discovery and tracking of previously unseen or hard-to-find small objects in orbit that could potentially collide with satellites. From its mountaintop perch at White Sands Missile Range in New Mexico, this revolutionary optical telescope, called SST for short, combines several groundbreaking technologies that are helping redefine what telescopes can do. SST has moved space situational awareness from seeing only a few large objects at a time through the equivalent of a drinking straw to a windshield view with 10,000 objects at a time, each as small as a softball. SST can search an area larger than the continental United States in seconds and survey the entire geosynchronous belt within its field of view, 1/4 of the sky, multiple times in one night. SST has enabled these game-changing capabilities by developing many technological firsts. For example, SST uses the most steeply curved primary telescope mirror ever made. This mirror enables SST to collect more light to see images across a wider field of view than any other space surveillance telescope. SST can see 10 times fainter objects in geosynchronous orbit 22,000 miles above the Earth's surface, than traditional telescopes. SST has the power to track small objects at greater distances than other telescopes in the U.S. space surveillance network that the Air Force operates. SST has added to our knowledge of space debris in GEO and has even tracked asteroids beyond the Moon. To hold this mirror, SST uses an innovative Mersenne-Schmidt design, which enables much more compact construction than traditional telescopes. In fact, SST is the largest telescope ever to use this design, which has also made it the quickest and most nimble large telescope in the world. SST's highly agile mount can rotate and tilt at 17 degrees per second to rapidly follow space objects. The telescope weighs in at 90 tons and its engines put out 38,000 horsepower, enough to drive 19 tractor-trailers, but are only as loud in combination as a microwave oven. SST's camera includes its own noteworthy inventions. SST developed the first ever curved charge-coupled device, or CCD, to provide clear imagery across its wide field of view, because traditional digital cameras with flat CCDs are unable to record images from such highly curved mirrors without distortion. SST has the fastest telescope camera shutter in the world and is able to take thousands of pictures a night. With these capabilities, SST offers unprecedentedly rapid search of small, faint objects in space. It can collect up to 1 terabyte of data each night and uses custom algorithms to shorten data processing timelines and provides same-day observations to the Air Force. SST's wide-open eye on the sky sees not just around the Earth, but also the solar system and universe beyond. NASA is already leveraging SST's capabilities to see very faint objects in a wide field of view to help provide warning of asteroids and other near-Earth objects. With 2.2 million asteroid observations in 2014, 7.2 million in 2015, and hopes for 10 million in 2016, SST has become the most prolific tool for asteroid observation in the world. SST has also discovered 3,600 new asteroids and 69 near-Earth objects, including 4 that carry a risk of possibly hitting the Earth. The U.S. Air Force, the historical steward of U.S. space situational awareness, is now poised to take ownership of SST and has announced plans to operate it in Australia jointly with the Australian government. As SST prepares for its move, DARPA is upgrading it to make it even more effective. In July 2016, DARPA installed an improved camera with an even wider field of view and increased sensitivity. This camera is designed to increase by up to 50% the number of complete scans of the GEO belt SST can perform each night. DARPA is enhancing SST's faint object detection algorithms to compensate for the thicker atmosphere and hotter, wetter climate at SST's new home. DARPA is also providing faster search capability for the U.S. military's space surveillance community and same-night follow-up of near-Earth asteroid candidates. SST's numerous technological breakthroughs and their potential to help augment space situational awareness capabilities both in the United States and Australia represent another success in DARPA's pursuit of its singular and enduring mission: to make pivotal investments in breakthrough technologies for national security. Since Sputnik first streaked around the Earth in 1957, man-made satellites have become the foundation for modern communication, Earth observation, and other critical military, civilian, and commercial functions. As satellites become more numerous every year, a threat grows with them. Man-made space debris, including spent rocket stages, defunct satellites, and fragments as small as flecks of paint. It is estimated that more than 500,000 pieces of debris currently hurtle around the Earth between 7,000 and 17,000 miles per hour, depending on their orbits. At those speeds, even the smallest impacts can damage or destroy satellites, increasing the amount of orbital flotsam and creating minefields in space that can remain unpassable for centuries. With the risk of space collisions accelerating, tracking debris is essential for warning of impending collisions. Some satellites can use that time to make small adjustments to their orbit or take other actions to protect themselves, but these capabilities are limited and some satellites lack them altogether. Tracking debris is the cornerstone of space situational awareness, not just to protect existing commercial and government satellites, but also to ensure that paths to critical locations in low Earth orbit, geosynchronous orbit, and orbits in between stay clear and safe for future space assets. For these reasons, the U.S. Department of Defense has made space situational awareness a top priority. The historical steward of this responsibility has been the U.S. Air Force, which operates the U.S. Space Surveillance Network, a worldwide network of 29 military radar and optical telescopes charged with observing and cataloging space objects to identify potential near-term collisions with orbital assets. To help the Air Force continue to provide the best space situational awareness possible, the Defense Advanced Research Projects Agency, or DARPA, has developed the Space Surveillance Telescope. From its mountaintop perch at White Sands Missile Range in New Mexico, this revolutionary optical telescope, called SST for short, combines several groundbreaking technologies that are enabling much faster discovery and tracking of previously unseen or hard-to-find small objects. SST has moved space situational awareness from seeing only a few large objects at a time through the equivalent of a drinking straw to a windshield view with 10,000 objects at a time, each as small as a softball. SST can search an area larger than the continental United States in seconds and survey the entire geosynchronous belt within its field of view, 1/4 of the sky, multiple times in one night. SST achieved first light and acquired its first images in February 2011. DARPA and Air Force Space Command completed SST's initial military utility assessment in 2012. And every year since, the telescope has become a more prolific and powerful tool for tracking small space objects. Air Force Space Command is now poised to take ownership of SST and has announced plans to operate it in Australia jointly with the Australian government. Australia offers a uniquely beneficial vantage point for operational testing and demonstration of SST's capabilities. From its new home, SST will provide key space situational awareness information from the Southern Hemisphere, an area of the geosynchronous belt that is currently sparsely observed, to the Space Surveillance Network. SST will also continue to provide NASA and the scientific community with surveillance data on transient events such as supernovas, as well as potentially hazardous near-Earth asteroids. In preparation for SST's move to Australia, DARPA has upgraded the telescope's camera, faint object detection algorithms, and search speed to make it even more effective. SST's numerous technological breakthroughs and their potential to help augment space situational awareness capabilities both in the United States and Australia represent another success in DARPA's pursuit of its singular and enduring mission: to make pivotal investments in breakthrough technologies for national security.